Today we're going to do Unit 4, Lesson 7. This is probably one of my favorite factoring topics of all. And I say that factoring, but it's probably one of my favorite algebra topics even. It's lots of fun. So we looked at how to factor out a GCF. And today we're going to look at a special way of factoring which you guys actually encountered in your homework yesterday. So hopefully you were able to get an idea. We're going to look at things that are called conjugate binomials, okay? These are binomials that are in the form of a plus b and a minus b. So something special happens when you multiply two binomials that are the same but just have a plus and a minus in between them. So that's what these all have in common. X plus 5, x minus 5, x minus 2, x plus 2, 4x plus 1, 4x minus 1. Even down here, 5x plus 2y, 5x minus 2y. So the two terms are the same. The difference is that one has a plus and one has a minus. So something special happens when we do this. Okay, so first we're going to just practice multiplying. And we're going to see what happens when we multiply these together. Okay, so just in the interest of saving a little time, I'm actually going to just use FOIL here so I don't have to draw the boxes out. But you guys can do whatever method you like. So this is x times x is x squared minus 5x plus 5x minus 25. The two 5x's cancel out, so this is x squared minus 25. Okay, take a look at the second one, see if we can figure out a pattern. X times x is x squared. 2 times x is 2x. Negative 2 times x is negative 2x. And negative 2 times positive 2 is negative 4. In between, we can see that the 2x and the negative 2x cancel out. So we get x squared minus 4. Seeing the pattern yet? Let's take a look at C. We're going to multiply the first terms. 4x times 4x gives me 16x squared. 4x times negative 1 is negative 4x. 1 times 4x is 4x. And then 1 times negative 1 is negative 1. And again, those middle terms cancel out. Negative 4x plus 4x. And I have 16x minus 1. So why don't you guys go ahead and pause, do the last three, and see if you can figure out what this pattern is. Okay, so let's see if you got the same answers. When you multiply these, you should get x squared minus y squared. Remember, when you multiply two variables together that aren't the same, you just put them together, literally. So x times y is going to be xy. Y times x is xy. This one was negative. Those cancel out. E, same thing happens. The two middle terms cancel out, and I get 4x squared minus 9. And then for f, I end up in the middle with negative 10xy and positive 10xy. Those cancel out, and I'm left with 25x squared minus 4y squared. So what is the pattern? What keeps happening each time? Each time you notice those two middle terms cancel out. And the reason why is because, well, each time you have a positive version of the number and a negative version, and that's why they keep canceling out. Okay, so the pattern, though, there's even more to the pattern. What do you notice about the first term? The first term is the first number, or first term, squared in each case, right? So the first terms here was x, that's x squared. X squared. 4x, 16x squared. X squared. 2x, 4x squared. And 5x, 25x squared. What about the second term? Well, same thing. It's the second term that you had squared as well. So the 5 squared was 25. 2 squared was 4. 1 squared was 1. Y squared is y squared. 3 squared is 9. And 2y squared is 4y squared. So, one last piece here. What do they all have in between the first and second terms? They all have a minus sign. So there is a pattern. Whenever you're multiplying two conjugate pairs, which means the two exact same binomials, but one has a plus and one has a minus, there is a pattern you can use. Now, when I was in high school, this is what my teacher used to say, okay? You square the first, square the second, and stick a minus in between. It's definitely not the most eloquent, but it has stuck with me now until I am in my 30s. So hopefully it will stick with you guys too. So that's the pattern. You square the first term, square the second term, and stick a minus in between. And you can do that for everything, even the complicated ones like this. So instead of going through and doing all the multiplication, what I can do is I can say 5x squared and 2y squared and stick a minus in between. That's the pattern. Okay, so what we're gonna do is, and of course it's written out here in algebraic terms, you were expecting to get a trinomial here, right? But we ended up with a binomial instead. So now, instead of doing these the long way, we're going to use this pattern we just learned, and we're going to quickly write the answers. And by the way, I'm sorry, I should have said this before. This is called the difference of two perfect squares. And these are conjugate pairs here. So let's practice. You have to first recognize, of course, that this is going to be the difference of two perfect squares by noticing that you have the exact same two binomials, just one is plus and one is minus. So I'm going to square the first is x. So I'm going to square the first, that's x squared. I'm going to square the second, 6 squared is 36. I'm going to stick a minus in between. And that is your answer. How easy is that, right? Let's try it for b. Square the first, that's going to be 25x squared. Square the second, that's going to be 4. Stick a minus in between. Done. C. Square the first, 4x squared. Square the second, 49y squared. Stick a minus in between. Done. Boom shakalaka. Okay. You guys try D through F. Pause, give it a shot, unpause and check. Okay, hopefully you got these answers. You square the first, which is 16, square the second, x squared, stick a minus in between. 16 minus x squared. Same here, 36 minus 25y squared. Keeping in mind that the variable was in the front for these, that doesn't mean it always has to be. You just follow the same pattern as your binomials. So if the constant comes first in the binomial, then you keep the constant first. So you literally just square the first, square the second, and stick a minus in between. Don't mess with anything else. Just leave it in the same order. Okay? So here too, square the first, that's 36. Square the second, 25y squared. Stick a minus in between. And the last one, same thing. You should get 100x squared minus 16y squared. Square the first, square the second, stick a minus in between. Okay? So now what we're going to do is we're going to reverse the process, because this is a special multiplication situation, and because it's a special multiplication situation, we can go backwards and we can factor something that's already written as the difference of two perfect squares because we know this pattern. So you have to, again, recognize. No one's going to ever really tell you this. You have to recognize. So you look at this and you're told to factor. Whenever you see this, you're going to see two terms, and you're going to hopefully think to yourself, the first thing is, let me check and make sure maybe these are the difference of two perfect squares. So in order to use this, first of all, it obviously has to be subtraction, because it has to be the difference of two perfect squares. So it must be subtraction. If there's a plus sign in here, then you can't use this, okay? The second thing you have to check is that they're both perfect squares. So this is very easy, but it does get tricky when we're dealing with exponents, okay? And I'll explain why quickly. When we're squaring exponents, when we're multiplying exponents by themselves, for example, x squared times x squared is x to the fourth, right? So x to the fourth is a perfect square. What happens if we do x cubed times x cubed? Do I get x to the ninth? No. I get, remember the rule is keep the base and add the exponents, so I get x to the 6th. So technically, x to the 6th is a perfect square. And the same thing goes for x to the 4th times x to the 4th. That's going to be x to the 8th. That's a perfect square. Okay, and then x to the 5th times x to the 5th is x to the 10th. That's a perfect square. So what are you noticing? There's a pattern here. All of any exponent that has an even exponent is going to actually be a perfect square, okay, when it comes to variables. So you got to be careful with that. So anyway, how do we do this? We've got a perfect square here, and 81 is also a perfect square, right? And remember, we're talking about perfect squares. We're talking about the numbers that we get. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81, 100, and so on. Those are our perfect squares. Now, hopefully you remember that when we did our co-op prep. So, in order to use the difference of two perfect squares, we're going to double bubble. We're going to take the square root of the first in the front and the square root of the second in the back. And we separate it with a plus and a minus. All we're doing is going backwards. So you're going to double bubble. The square root of x is x, so you put an x in both fronts. The square root of 81 is 9, so this is a 9. And you separate it with a plus and a minus. We're just going backwards, right? Because if we had seen this, we would have squared the first, squared the second, and stuck a minus in between. So that's it. This is the simplest type of example. And of course, it gets a little trickier. So, first thing we do, we see subtraction. We want to make sure these are both perfect squares. 9x squared is a perfect square because 9 is a perfect square and x squared is. And 4 is as well. So we double bubble it. We figure out what's the square root of 9x squared. So what is it? What times what gives us 9? That's 3. And x times x gives us x squared. So the square root would be 3x. So the 3x's go on the front. The square root of 4 is 2. Plus, minus. That's your answer. And of course, you can always check. 3x times 3x will give me 9x squared. Okay? Part C, same thing. The only difference here is that your constant is coming first. Make sure you don't change the order. Double bubble. Square root of 25 is 5. And the square root of y squared is y. Plus, minus. Okay, and again, you can always check your answer by going backwards. Square the first, square the second, stick a minus in between. And then you'll know that you're right. Okay, so why don't you try D through F on your own and then check your answers. Okay guys, so for the first one, you should get 2x plus 9y, 2x minus 9y. And again, you can check by going backwards. Square the first, you'll get 4x squared. Square the second, you'll get 81y squared. And stick a minus in between, you will get that. So this is the right answer. For part E, the square root of 121x is going to be 11x. X squared, sorry. So, and then the square root of 1 is 1. So it should be 11x plus 1, 11x minus 1. And you can check by squaring the first, squaring the second, and sticking a minus in between, and you get the same answer. And finally, part F, 1 minus 4x squared. That's also a perfect square. So that's 1 plus 2x and 1 minus 2x. Okay, guys? So these are some simple examples. It does get a little bit trickier than this when it comes to these exponents. So look out for these in the homework, okay? We are going to do, after we finish the second way of factoring, we're going to do a whole day of just reviewing all the different ways of factoring. So if you're stressing out about this, don't worry. This is one of my favorite things. I hope that you also enjoy it. If you're having trouble with finding the square roots here, for these ones, try to remember you can write a list of perfect squares on the side, and you can even write this list of perfect exponent squares if you need to, okay? And then when in doubt, just always write it out and check it and see, 11x times 11x will give me 121x squared. okay? And if you have any questions, just let me know on Google Classroom. Have fun.